Dear attendees of this year's Eurodyn conference, welcome to our presentation. I hope this presentation finds you well under these special circumstances. My name is Alyosha Sander. I'm the guy with the red beard in the center of the left image. My co-author is Christian Meinhardt, whom you can see on the right, as well as Professor Tobin, who supervised this work. Special thanks goes out to my colleagues Andreas Haselsteiner on the left of me and Michael Janssen on the right of me, without whom this project would not have been feasible. Offshore wind will become one of the pillars of the future of energy generation. It also just got economically viable, meaning first projects are realized without any subsidies. One key challenge in offshore wind is installation and maintenance. The offshore environment is extremely harsh and challenging for both humans and materials involved. Installation usually takes place in several steps and usually takes over 2 years. The first part of the turbines is the foundation, in our case monopiles. On the monopile sits the transition piece, which is the yellow structure visible in some of the figures. After the transition piece is installed, the actual turbine follows. Turbine installation starts with installing the tower, which you can see in subfigure A. After the tower is installed, the nacelle is picked up and installed, as can be seen in figures B and C. Finally, the blades are installed. Blades are installed consecutively, which is depicted in figures D and E. Single blade installation, as this process is usually denoted by, is susceptible to wind and wave induced motion between the blade root and the rotor hub. This situation is shown specifically in figure E. Wind and wave loads lead to strong restrictions in the installation process, because due to these relative motions, single blade installation is thus only feasible under certain environmental conditions. If the wind is too strong or the waves too high, the relative motions between the two components become too large and single blade installation subsequently fails. All photos are from the installation of the wind farm Triennial Wind Park Borkum 2, which is the installation campaign that we used for our measurements. The wind farm consists of 32 Senvion 6M152 turbines and is located in the German Bight in the North Sea. The following videos shall illustrate the challenges associated with single blade installation. From the videos, it is difficult to tell where the motions are coming from. So, let's take a step back and analyze the situation that we saw in the videos. The partially installed turbines, consisting of tower, nacelle, and rotor, have already been installed on the monopile. Wave loads induce motions in the wave direction, and wind loads induce both loads in streamwise and lateral direction. Both wind and waves are chaotic in their nature, and thus the loads somewhat resemble that chaotic character. However, the difference in fluid density is a factor of approximately 800. To better understand the phenomenon that we were facing, we used custom-made sensors that recorded accelerations as well as GPS to measure the vibrations seen by the turbine as well as by the blade. Preliminary analysis showed then that only the turbines vibrate, while the blades showed very little movement. Therefore, within this frame of this publication, we only analyzed accelerations from the helicopter hoisting platform, a platform atop of the nacelle. The sensor that was placed there is referred to by the abbreviations S1, as can be seen in figures A, B, and C. More data at different positions was recorded, which will be made available in another publication. Throughout the execution of the wind farm installation, a tuned mass damper, or short TMD, was installed the nacelle, of each turbine undergoing installation to reduce the relative motion seen between blades and rotor. In order to measure the behavior of the tuned mass damper, an additional sensor was then placed on the mass of the tuned mass damper. This sensor is denoted as S2. For the post-processing of the recorded data, all data was resampled to 30 Hz. Accelerations were then filtered using a third-order Butterworth bandpass filter, where cutoff frequencies were between 0.1 and 1 Hz for the lower and upper frequencies respectively. Finally, accelerations were then numerically integrated using a second-order trapezoid scheme. This slide visualizes the post-processing. Raw and filtered accelerations from the fore and aft and side directions are shown below, and on the left-hand side of the nacelle. The ball of wool-like structure that can be seen in the center of the nacelle is a Lissajous figure of the positional vector of the turbine. It corresponds to the trajectory of the nacelle when viewed from above. Note that the trajectory is not to scale. The purple arrow within this ball of wool-like structure shows the deflection of the turbine as seen by an external observer. This deflection is the magnitude of the positional vector and shown as a time series in subfigure C. This temporal signal was then decomposed into 30-second windows where the average deflection was calculated. These 30-second mean values were then used to create scatter plots. These scatter plots then show the correlation between, for instance, a significant wave height and deflection of the turbine. This is shown in subfigure D. Please note that in the later results, the time frame used was not 30 seconds, but 10 minutes. Finally, subfigure B shows the GPS elevation profile from the blade. This illustrates how the timing of the installation process was monitored. Let us now look at first results. Here, turbine deflection from one of the 32 turbines that underwent installation is shown. The deflection is normalized by tower diameter. The white line corresponds to the 10-minute rolling mean of the instantaneous deflection. The black line represents the single blade installation limit. If the instantaneous deflection was above it, the installation became likely to fail. 3 different time frames are visible for which the instantaneous deflection stayed below the installation limit. For the rest of the installation, single blade installation was not feasible as the instantaneous deflection was too large. On this slide, the same parameters are shown. However, this time, the turbine was equipped with a tuned mass damper. Instantaneous deflection rarely reached levels higher than the installation limit. Variations in the deflection are also much smaller compared over the complete time, as also becomes evident when looking at the 10-minute rolling mean. Hence, for the complete time period, single blade installation was feasible. However, without considering the environmental parameters, the previous recording and this current recording cannot be compared. Therefore, we decomposed the time series from the turbine without a TMD and the time series for the turbine with a TMD into 10-minute windows, and combining it with the 10-minute mean significant wave height from both the winds. This allows to compare the state of the turbines as well as the impact of the tuned mass damper on the 10-minute mean deflection. Evidently, for the turbine with the tuned mass damper present, the 10-minute mean deflection is much lower than for the turbine without the tuned mass damper present. This holds true for the turbine with the tuned mass damper present, even at higher waves. On this slide, you can see all the 10-minute mean deflections that were recorded on turbines undergoing installation without a tuned mass damper. These measurements are represented by the red markers. 10-minute mean deflections of turbines that had an active tuned mass damper are represented by the blue markers. The range of observed significant wave heights goes from below 0.5 meters to almost 4.5 meters. Of course, these data include time periods where no single blade installation was attempted. Evidently, less data points are available for time periods with an active mass damper. This is because single blade installations where the tuned mass damper was active was only attempted for significant wave heights between 1 or 2 meters. Nevertheless, it becomes apparent that significant wave height has very little impact on the 10-minute mean turbine deflection if the tuned mass damper is active. For the same given significant wave height, turbines without a tuned mass damper depict a 10-minute mean deflection that is between double and more than sixfold that of a turbine with additional damping. In this slide, we depict the 10-minute mean deflection as a function of the wave peak period. No clear dependence on deflection on wave peak period can be observed. Still, turbines where a tuned mass damper was active showed a strongly reduced 10-minute mean deflection. Last but not least, we show the 10-minute mean deflection as a function of the wind speed. With an increase in wind speed, deflection increases as well. However, for a given wind speed of, let's say, 10 meters per second, deflection can go from between 0.5% of tower diameter to almost 3% of tower diameter. Again, for turbines where an active tuned mass damper was present, deflection stayed well below 1% of tower diameter for the range of observed wind speeds. Let's look on how the turbines undergoing installations behave in the frequency domain. In the upper two figures, the hatched area represents the time period within which the tuned mass damper was activated. The left-hand side shows the fore-aft acceleration, and the right-hand side shows the side-side acceleration. The lower two figures show the spectrogram of the accelerations. With the activation of the tuned mass damper, the intensity of the frequency signal drops significantly. When the first blade is added to the tower, a visible dip in the frequency appears. Because the blade yoke that is used to install the blades is quite heavy, the point in time when the yoke releases the blade can also be observed. The same behavior can be observed for blade 2 and 3 respectively. After all three blades are installed, the eigenfrequency is observably lower than prior of blade installation. Using operational modal analysis, we calculated the damping of the turbines with and without an active tuned mass damper. Without the tuned mass damper, the structural damping ratio of the turbine is approximately 0.5%. Once the tuned mass damper is activated, the structural damping ratio increased to an average of 2.5%, with outliers just below 2% and well above 4%. So, what does it mean for single blade installation? First of all, as expected, we observed a strong correlation between deflection and significant wave height, as well as deflection and wind speed. This is of course because wind speed and wave height are strongly coupled in the North Sea. From the recordings alone, it is not possible to decide whether wind or wave loads are mainly responsible for the observed motions of the turbine. From correlating different attempts of single blade installation with the observed 10-minute mean deflection, we were able to learn the single blade installation limit, which is approximately 3% of tower diameter. As this limit corresponds to waves with a significant wave height below 1 meter or wind speeds below 5 meters per second, very few time windows were available during the first half of the installation to install the blades. A tuned mass damper significantly reduced the observed deflections, which led to faster installations at higher waves and stronger winds. The increase in damping from approximately 0.5 to 2.5% explains the observed reductions in deflection well. We therefore think that a tuned mass damper is a feasible and flexible option to increase the success rate of single blade installations at higher significant waves and stronger winds. Future work should focus on the analysis of the observed trajectories of tower vibrations in order to enable better predictions of suitable installation windows. Because we hypothesize that the deflection alone is not sufficient to predict whether an installation will be successful or not. We thank you, the audience, for your attention, and we thank our partners from the industry who enabled this measurement campaign.